Hello everyone, my name is Aminul. Today I'm going to talk about scanning electron microscope as part of the final project for MEEN 680 optical technique for engineers. Let's first start with the background of electron microscope and why do we need it. In the following figure, we can see the resolving powers of various types of microscope. From the figure, it is clear that the resolving power of optical microscope is around 250 nanometers. That is around half of the wavelength of visible light. The resolving power is limited due to the diffraction limit. Electron microscopes were developed to observe the features that are smaller than this limit. So electron microscopes utilize electron beams. Electron beams have a much shorter wavelength, so much higher resolving power. From the de Broglie's relationship, we can see that the wavelength of the electron is dependent on its velocity. So the higher the velocity of the electron, the more resolving power it has. Moreover, the depth of field of a scanning electron microscope is much larger than that of an optical microscope. So, a scanning electron microscope projects and scans a focused stream of electrons over the surface of a sample and collects the various signals that are produced during the interaction. These signals are then converted into image using specialized detectors. So here we can see the various components that are used to achieve that. So for the first component, we have the electron gun that produces high energy electrons. These high energy electrons are then accelerated by a series of positive anodes. The velocity of the electron beam is nearly 70% of the speed of light. Next, we have a series of electromagnetic lenses. These electromagnetic lenses can be divided into two parts, condenser lenses and objective lenses. Next, we have a scanning coil that deflects the beam of electron to draw a raster pattern on the sample. And finally, we have detectors that basically converts the signals produced during the interaction between the electron beam and the sample surface. The detector signal then used to obtain information about the sample's surface topology and composition. Let's talk about different parts of this scanning electron microscope. Let's start with the electron source. ACMs typically utilize various types of electron emitters. Among them, field emission guns are the more commonly used. Field emission gun is a wire of tungsten with a very sharp tip that is less than 100 nanometers. It uses field electron emission to produce the electron beam. Basically, there is an electrical field between the tungsten tip and the extractor. So, due to the electric field, electron tunnels out of the sharp needle of the tungsten. Then this electron beam is accelerated using a series of positive anodes as you can see in the figure here. Next, we have electromagnetic lenses. Electromagnetic lenses basically guide the beam of electrons. It is very much similar to converging and diverging lenses in an optical setup. So, electromagnetic lens is basically a copper coil. When electricity is passed through the copper coil, that induces a magnetic field. An electron beam moving through the magnetic field experiences a force called Lorentz force. This Lorentz force acts perpendicular to the motion of the electron beam. So, as the electron moves through through this magnetic field, the Lorentz force guides the electron beams towards the optical axis. The further the electron is from the optical axis, the higher the force is acting on it. So the more the electron is guided towards the optical axis. So in a traditional ACM, we have a series of electromagnetic lenses, and these are divided into two parts, as I said earlier, condenser lenses and objective lenses. Condenser lenses define the size of the electron beam. Basically, they reduce the diameter of the electron beam. And the objective lenses basically focuses the electron beam onto the sample surface. The work of the scanning coil is to produce a raster pattern onto the sample. So scanning coil deflects the beam in the X and Y axis following the raster pattern. At every point, the detector counts the electrons coming from the sample, and the intensity of the signal is then mapped to a screen. And the smaller the scanning area and the higher the magnification we get. Next, we'll talk about the interaction between the electron beam and the sample surface. So the interaction between the electron beam and the sample surface creates a teardrop shaped region. So there are various types of signal. First, we have secondary electrons. These are low energy electrons that are from the sample surface due to the inelastic interaction between the electron beam and the sample. The intensity of the secondary electrons is dependent on the local topology of the sample surface. So a secondary electron signals provides us with the topological information. Next, we have backscattered electrons. There are high energy electrons resulting from the elastic interaction between the sample surface and the electron beam. These backscattered electrons provides us information regarding the surface composition of the sample. Next, we have X-rays that results from the collision between the electron in the orbit of the sample and the electron beam. These X-rays helps us characterize the sample element. So let's now look at some ACM images. On the left, we have the image from secondary electron, and on the right, we have the image from backscattered electron. The secondary electron image provides us information about the topology as stated earlier. On the other hand, in the backscattered images, we have some dark and light regions or bright and dark regions. So it tells us that in the sample, there are two different types of elements or two different uh, types of materials that basically resulted in the contrast. Typically, higher atomic number elements results in more brightness compared to lower atomic number elements. And next we have X-rays. As I said earlier, X-rays are produced when electron is knocked off its orbit and another electron fills that void, and that emits some X-rays, and the emitted X-ray is characteristics of the element of the sample. So each different types of elements will have different characteristics X-rays, and from that X-ray signal, we can identify which element is present in the sample. So in ACM, we are scanning in two-dimensional, but the ACM images, as you can see in the following figure, looks 3D. How is that possible? That is basically due to the edge effect. What is edge effect? It is basically if you have a flat surface, few electrons escape from that surface. But if you have an edge or a peak, more electrons escapes that surface. That results in brighter edges. So the brighter edges helps us to have a 3D-like image. Next, we'll talk about this figure. Here we can see the entire figure is on focus or in focus, but we don't typically see a large large depth of field in a typical optical microscope. So how is that possible? Again, it is because the ACM has much higher depth of field. This much higher depth of field is the result of narrow and parallel electron beam. So this allows to see the entire 3D structure of the complex object in sharp focus from front to back. It is similar to a pinhole camera where the light is entering to the sample using a very small hole. So ACM is usually used in various sort of application. The more prominent applications are microstructure characterization. ACMs are used to identify different types of materials or different type of components in a sample. It is used for semiconductor inspection to find out the defect and deformation. And another important use of ACM is for nanostructure characterization, as you can see in the following figure. So ACM is a very versatile tool, and it is used almost in every aspect of science and engineering. Thank you for listening to my brief presentation on scanning electron microscope.